Hello, I'm David. I'm one of the lecturers in the Maths Learning Centre at the University of Adelaide, and this is a rough and ready lecture about using derivatives to know about the shapes of functions. Okay, so there's four features of a graph or a function that I would like to talk about. Two of them don't really have anything to do with derivatives, and the other two, well, when they first started, when I first see them, they don't have anything to do with derivatives, but I can find out things about those features using derivatives. So I'm going to start out by looking at all of these things without using derivatives, and then coming back and seeing how derivatives deal with the last two. But the first two I want to deal with are just about the function itself and not its derivative. And so it begins with, just a second, let me write a title. Features of functions. Okay, the first thing is places where the function is undefined. Okay, some functions will work no matter where. No matter what x's you put into them, you'll always be able to find an answer. And some functions, when you put x's or whatever the letter is into them, sometimes you won't be able to find an answer. That's called being undefined. So just as an example, if you have f of x is equal to, say, x to the 5 minus x plus 7 cubed, that's always defined no matter what x is. No matter which x I think of, I can always sub that in and find an answer. And so I can just say always. Okay, but on the other hand, some functions, for example, this, are not always defined, mainly because you can't divide by 0. So if x is 6, then I'll have 13 divided by 0, and, well, dividing by 0 doesn't mean anything. There's no answer for that, and so it's not possible to figure that out. It's called being undefined. But any other number other than 6 is going to be fine. If I put in 5, I'll get 12 divided by -1, and that's minus 12. It's a perfectly good number. So the only place where this is undefined is when x is equal to 6. So these are two very common kinds of functions that I've drawn here. This one is a polynomial. If I expand it all out, it will be powers of x and timesing by constants and adding and subtracting. This thing has a polynomial on the top and a polynomial on the bottom. It's called a rational function. And polynomials are always defined, and rational functions are defined everywhere except where the denominator is 0. So I'm actually going to write that down. That's a proper feature of these kinds of functions. Polynomial is always defined. A rational function which is found by dividing two polynomials is defined everywhere except where the denominator is 0. So I'm going to show you some graphs of those things on Desmos. That's how the Americans say it, Desmos. So here is a polynomial. It's a perfectly good polynomial. It's always defined. For every x, there's always a y. Well, on the graph a y, I mean, but it's f of x. I can calculate it. Even for things where it goes off the graph. So over here, when x is, say, -2, it looks like there's no value there, but if I zoom out far enough, yes, it does actually have a value. It's just it's very low down. Oh, where's my mouse gone? Okay. And this graph is, there's three graphs there, and I've turned two of them off so you can't see them. This one has issues when x is 3 and when x is 8. So it's a perfectly good rational function. The top is a polynomial, the bottom is a polynomial, because when I expand it out, I've got powers of x. It is undefined when the bottom is 0, and the bottom is 0 when x is 3 and when x is 8. And what happens to the graph when you do that is you get these funky things where it goes up and down really fast. And this place where x is equal to 3 and this place where x is equal to 8, they are the places where the function is undefined. And you'll notice when I draw them in that the graph, as I get closer and closer to this line, the graph goes up very fast, and it gets closer and closer and starts looking more and more like this line. And same here. So this vertical line is called a vertical asymptote. And an asymptote is any line that the graph seems to get closer and closer to as you move further out, or further in, or further up. The word asymptote literally means flying together. Possibly not flying together. Anyway, the sim is together. The is the same as the middle of helicopter, and the beginning of pterodactyl, and that means wing. And so you have flying together. So the curves fly close to each other, but they never actually quite meet. Okay, and all of these have asymptotes at the same places. This one still has x minus 3, x minus 8 on the bottom, but it will look a little different. So this one went curving up and then downwards and then outwards that way. This one has a different shape, and this one still going to work. This part's a rational function, this polynomial, still only undefined at the place where the rational function has issues, and this one's really funky. It's a bit more like this one, but slanted. Okay, but all of them have that property that there's asymptotes at that spot. And what I'm really interested in is which way do these up and down bits point. That would be a really useful thing to be able to do. And I can reason that out based on some reasoning about what happens when x is very close to the value of the asymptote. So I'm going to do it on the paper. But first I'm just going to write down that fact that I just said. So when a rational function is undefined at x equals k, the line x equals, with equation x equals k, it's a vertical line, right? Is a vertical asymptote. Now, you may think, well, just a second, David, you said there's a vertical asymptote. Are there other kinds of asymptotes? There are. You may notice in these graph here, this function seems to approach being on a line here. That line's actually y equals x. That's called an oblique asymptote, and there are such things as horizontal asymptotes. So this function gets closer and closer to the x-axis, and the x-axis is aligned just as anything that's a horizontal asymptote. But I'm only interested in vertical asymptotes today. So, how are we going to decide which way up it is? And the easiest way to do that is via an example. So e.g., let's do my function is going to be called x squared plus 1 over x take 1. Okay, so I know it's undefined. Sketch a graph showing vertical asymptotes. So I know it's undefined when the denominator of any of the rational function parts is 0. And so the denominator of this bit is 0 when x is 1. So f of x is undefined when x is equal to 1. And so there's a vertical asymptote at x equals 1. Now I should say I have made a technical error here. Technically, sometimes there isn't an asymptote when the denominator is 0, and that tends to happen when the denominator and the numerator are both 0 at the same time. So I should just say that's called a vertical asymptote. It's technically only a vertical asymptote if the numerator is not 0 at the same time. So note so if they're both 0, then something else happens. But that I don't really want to go into that right now. Okay, but I just felt it was important to say it. So f of x is undefined when x is 1, so there is a vertical asymptote at x equals 1. And the numerator is not 0 at that spot, so there really is a vertical asymptote at x equals 1. And so I do know that when I draw the graph, it'll be something like this. There's 1, like that. And it's not defined there, so I'll just put an open circle there just to absolutely make sure that we don't use that point. So I want to know, there's 4 options for what could happen. It could go up here and up there, or it could go down here and down here, or it could go up here and down here, or down here and up here, and I want to know which one it is. And one way to do that is to investigate what happens when x is close to 1, but above or below it. So I could say if x is close to 1 but below, e.g. X is like 0.999, okay, I can figure out whether it's going to be going up or going down. So when I get closer and closer, is it going to shoot upwards or is it going to shoot downwards? That's the question we want to know. Well, then x minus 1 is close to 0, but it's negative. Okay, so if we go 0.999 minus 1, I'll get minus 0.0001, sorry, 001. And so I've got something that's close to 0 but negative. And if I go 1 divided by a number that's close to 0, it will be an extremely huge number. But in case I'm dividing by a negative number that is extremely huge, it's going to be an extremely huge negative number, and so therefore is going to be going downwards. And so it's going to go over to the next page. And so 1 over x minus 1 is large and negative. Okay? So a short way to say what I'm about to say is thus, if x goes to 1 from below, or the official word is approaches, one from below, as x goes to approaches 1 from below, then f of x will go to large negative, so negative infinity. Okay, so what that means is that my graph is going to be going negative infinity when it comes in here. I should probably put it further down than that because I don't really know how far away it's going to be. Like that. Okay, so I'm just drawing these pictures one after the other so that you can see how it's built up, but normally you just put it all on the same graph. Okay, now if x is close to 1 but above, e.g. x is like 1.001 or 1.0001 for example, then x minus 1 is close to 0 but positive. And so therefore 1 over x take 1 will be 1 over something close to 0, which would be a really huge number. If I divide by 0.001, I will get 1,000. Positive. And so thus, as x approaches 1 from above, then f of x goes to large positive, so positive infinity. Okay, so my graph is now going to look like, there's 1, it goes that way, and if I come in from above, it goes that way. I don't really know what the rest of the graph is doing, actually, and that's what the whole rest of this stuff is about, to try and figure out what the rest of the graph is doing. But here, that's how one way of deciding what it's doing on either side of an asymptote. You will find a slightly faster way of doing that if you want to know some other information as well a little later. So just one last thing that I want to talk about. It's just one thing I just want to mention. It's not a big thing. It's that we can actually figure out what an idea of what the rest of the function is doing by thinking about what happens not when x is close to 1, but when x is really huge. So look at this. Here's the function. If x is a very, very large number, like 1,000,000, then 1 over 1,000,000 minus 1 is approximately 0. So when x gets bigger and bigger, this bit gets close to 0, and so it gets close to whatever x squared is. And similarly, if x is a really big negative number, this will be close to minus 1,000,000,000th or whatever, and it'll be close to whatever x squared is, but it'll be a little bit less. And so we can talk about that in a useful way. We can say, as x goes to very large numbers, so infinity, it's never actually equal to infinity, it just becomes very large. Then 1 over x minus 1 will get close to 0, but it'll do that from above because it'll be positive. And so therefore the f of x will get closer to x squared from above. Now this little plus at the top only applies to numbers, so I need to actually use the words when I talk about a function. And as x goes to big negative number, then 1 over x take 1 goes to 0 from below, and so therefore f of x will go to x squared from below. And so I can finally have a decent idea of what this graph is like. So here's 1, and we know that there's no points there. And we know what x squared looks like. It sort of looks like probably higher than that, but anyway, so this is 1 here. It's not drawn to scale. And we know it goes down here, and it goes up here. And we know that it's always above x squared, and it gets closer and closer to x squared. And we know it's always below x squared, and it gets closer and closer to x squared as well. And so it'll look something like that. something weird's going on here, and that's what the rest of my calculus is for. I can at least figure out what this point is. I should just say, you know, the y-intercept is when x equals 0. So f of 0 is 0 squared plus 1 over 0 minus 1, which is, that's 0. 1 divided by -1 is -1. And so that's actually -1 there. I actually picked the right spot. Okay, well, a useful question would be, what's this point? Because we want to be accurate. Because I can see it's below the x-axis here, and above the x-axis here, and above the x-axis here, and it crosses over the x-axis at that point. And that's the next feature we're going to talk about. Like, where is it above and below the x-axis? Okay. 2. Let me just go back and add to this title here. Asymptotes. Okay. So 2, we're going to have above and below the x-axis. Okay. So, let me go back to my computer. And I'm actually going to go back to this one. So this graph is below the x-axis over here, and I can't see it, but way down below it's all still negative. Below the x-axis over here, it's above the x-axis here, it's below the x-axis here, it's above the x-axis here, and it's below the x-axis here again. So I can see where it is in terms of above and below the x-axis. And it would be useful to know what the feature of the function values is that goes with that. But it's pretty obvious. These are all the positive y values, and these are all the negative y values. So whenever the y value, or the function value, f of x, either one, whenever that's positive, it'll be above the x-axis. Whenever it's negative, it'll be below the x-axis. And whenever it actually crosses the x-axis, it'll be 0. Some functions, like this one, will be below the x-axis, it's above the x-axis, then it's below the x-axis for this little tiny bit here, then it's above the x-axis, then it's below for a little tiny bit here, then it's above the x-axis. And there's issues at the places where it's undefined. And so those asymptotes are going to be interesting. You'll notice that on one side of the asymptote it's negative here, but on the other side of the asymptote it's positive, and that'll happen a lot of the time. But it can be negative on both sides as well, actually. So watch what happens when I do this. See, positive on both sides of that asymptote now. So it is possible. Okay, but importantly, let's go back to this one, which is a little less funky. I know that the y-coordinate, or the function value, will be positive when it's above and negative when it's below, and it will cross the x-axis when it's, well, crossing between positive and negative. That would be when it's 0. So I can write all that down. So I'm just going to put in brackets here. Positive and negative. Okay, so if f of x is greater than 0, the graph is above the x-axis. If f of x is less than 0, graph is below the x-axis. If f of x equals 0, the graph has, well, those places where it crosses the x-axis are called X-intercepts. has an x-intercept. So the reason I was so formal about this is that you'll notice that feature of the graph goes with algebra feature, number feature of the function. And that's what we're going to get to soon. Okay, so that's all well and good, but how would you figure out where it was positive and negative? I can definitely figure out where it's equal to 0, so I could just find the function, make it equal to 0, and I've got an equation, and I can solve that equation, and it'll tell me when it's equal to 0. But I want to know, when is it positive, when is it negative? Well, it turns out that if it's equal to 0 at two places, and it's not equal to 0 anywhere in between, well, it can't be both positive and negative in that zone, because if it was positive and negative, it would cross over the x-axis in between. Now, that does require my function to be continuous, meaning that I can draw it without lifting my pen off the page. It doesn't have one of those asymptote things. So I'm just going to have to include that in my reasoning as well. Okay? Some functions are not continuous. They sort of go up to a point and then jump like that. We're not really going to talk about any of those. It's actually quite hard to describe those with a formula. And if you do any future maths, you might do some of that actually. But today I'm not going to cover those. So also, I was standing too still and the lights turned off in my room. Also, if f of x is continuous, on an interval, so when I say interval, I mean the space between all the x's between one number and another. Okay, a and b, it doesn't really matter what the a and b are. And there are no zeros, or discontinuity, and no places where it's undefined. Technically, I don't need to say that because f is continuous. If it's undefined at a spot, it's not continuous because you have to jump over that to get to the other side. But I just wanted to explicitly put it in there anyway. No places where it's undefined. Then either f of x is positive for all x in the interval, or f of x is negative for all x in the interval. Now it seems like a lot of stuff to say. This is the very formal maths version of what you saw. Well, it can't be above the x-axis. If it doesn't cross the x-axis, then it has to be either all above or all below. And that's what this means. So if you like, i.e. it doesn't cross the x-axis, it has to be all above or all below. But again, I'm making a point that I can use mathematical features to tell me about graphical features, and the theorems and the definitions. Theorems are things that are true, provably true. The theorems and the definitions will match up with those features, but they have to be. Theorems definitions are written in terms of the algebra and the calculus, and the definitions are too. Okay. So what does that mean? Well, it's easier to do when I do an example. So let's see. So for example, let's find where f of x, which is equal to x to the 4. Actually, do you know what? I'm just going to... That's all right. I'll do that later. X to the 4 minus 5x squared plus 4 is positive and negative, and state the x-intercepts of the graph. Okay, so I saw this, I'm imagining that I've seen this in like an assignment question or an exam, or some random person's run up to me in the street and asked me to do this thing. So I'm going to respond in ways that match the question. So I'm going to need to figure out where it's undefined first, and then where it crosses the x-axis, so where it's equal to 0. And then I know that between those points there aren't any places where it's 0 and places where it's undefined, so it's going to be all positive and all negative. So I'm only going to need to find out what it is for one point in those zones, and if it turns out to be positive for that one point, well, I know it's all positive or all negative, and since it's one positive, it must be all positive. And that's the sort of reasoning I'm going to go through. So it's a polynomial, so it's always defined. Okay, and we also need to find where f of x is equal to 0 in order to do what I'm about to do. So, well, that means that x to the 4 minus 5x squared plus 4 has to be 0. All right, well, if I want to solve an equation with a polynomial like that, the best plan is probably to factorize it. Quartics, it's technically possible to factorize them, but the formula is pretty awful, so I wouldn't expect most of the time for anyone to do that. So if someone ran up and asked me this, or if someone asked me in an assignment or an exam, I would think that there'd be some sort of trick I could use to factorize this. Well, the only things I really know how to factorize are things that all have x's in everything, or they have something in common, which I can pull out, and that this doesn't. Or quadratics. I know how to factorize a quadratic. X to the 4 is x squared squared. And so if I do that, this is a quadratic. It's something squared minus 5 something plus 4 equals 0. So I can actually solve to figure out what x squared is. So I've got two options. I can attempt to just factorize it directly by imagining things that multiply to give 4 and add to give minus 5, or I could use the quadratic formula. Or I can see it. Well, if I do 1 times 4 is 4, and 1 plus 4 is 5, but I want a minus 5. So minus 1 and minus 4 will do it. Okay, so now that these two things are equal to 0, and they multiply together, the only way to multiply things and get 0 is if one of those things is 0. In the USA, they're fond of calling that the null factor law, but most, and it's catching on in Australia a bit, but most people, when they do this, they don't even mention it, they just do it. So therefore x squared minus 1 is 0, or x squared minus 4 is 0. So x squared has to be 1. Now, if I do the square root, I'll get 1, but of course, if x was a negative number, it could have been minus 1, and when I squared it, it would give 1 as well. So x squared is 4, x squared, no, I want to get rid of the squared, plus or minus the square root of 4, which would be 2. Okay, so I've found all the x's that produce 0 when I put them into the function. They're called the zeros, and so I might as well say that. So the zeros are x equals minus 2. I'm going to pop them in order of size, order on the number line like that. I could say that the x-intercepts are that. Technically, when you say the x-intercepts, you should say where they are, because they're locations. So the x-intercepts are at these places. And some people, when they ask for x-intercepts, prefer you to give the actual coordinates of a point, since it's technically on the graph, which has both x and y coordinates. I personally don't care, but if you're ever in a situation where you've got a teacher who does care, then make sure you check to see if they do. But I'm going to pop it in, so the points are minus 2, 0, because, well, f of x is 0, right? Minus 1, 0, 1, 0, and 2, 0. And also, they're on the x-axis, and on the x-axis, all the y-coordinates are 0. Okay, so I found the x-intercepts. Now I need to figure out where it's positive and negative. And I know that between the places where it's 0, it'll be all positive or all negative. And what most people do is they draw what they call a sign diagram. For f of x. So you need to say what it's a sign diagram for, because there are other calculations that you might do that will tell you, some other calculation and what the plus or minus is of that. And we want to specify that it's the plus or minus of this formula. So what we're going to do is a little bit like a graph. We will put the locations of our points. They don't actually have to be equally spaced. It's just a diagram as opposed to a graph. And up the top, we're going to put pluses and minuses to indicate what f of x is, whether it's plus or minus. So it's a little bit like a graph, but not quite. And I'm just going to put dots here because it's traditional to put a dot every place where it actually is equal to 0. And you normally put an open circle at a place where it's undefined. Okay, so in order to write this sign diagram, I'm going to need to figure out whether it's plus or minus in each of these zones. If it is plus here anywhere, it will have to be plus everywhere because there's no zeros in this zone, as I just said earlier. So I just pick points in those zones. So I'm just going to need to have that function nearby. So that's the function there. So a point in this zone, I need something that's easy for me to calculate the powers of, and I can actually do that really well with minus 10. Minus 10 to the power of 4, minus 5 times minus 10 squared plus 4 is 10,000 minus 500 plus 4, which is positive. So this is plus with the VE from the end of positive, and so that'll be a plus. And something between minus 1 and minus 2, I don't really have a choice, so I'm going to have to do minus 3 on 2. Minus 3 on 2 to the 4 minus 5 times minus 3 on 2 squared plus 4. Well, I guess 3 to the minus will go away when I do a power of 4. 3 to the 4 is 81 on 16. 5 times 9 on 4. Plus 4. Okay. So this is 81 on 16. This would be 45. But if I want to add it to the 16, I should be going multiplying it by 4 as well. So 4 times 45 is 180 on 16, plus 4 times 16 would be 64 on 16. And that is totally going to be negative. Okay, so that's negative. This zone I need to pick a number in there. 0 is a really good number in there. 1 0 to 4 times 5 times 0 squared plus 4, which is positive. F of 3 on 2 and 2 to the 4 minus 5 times 3 on 2 squared plus 4. Actually, look at that. This is going to be exactly the same answer as this because the minus went away when I did power of 4 and it went away when I did the power of 2 as well. So this is positive. Okay, sorry. Negative. That's what it worked out to before, wasn't it? Yep. And f of 10, I guess, will do well. So that'll be positive as well because we already did that. And so there's my sign diagram, and it tells exactly when things are positive and when they're negative. And so if I want to answer the question of where is it positive and where is it negative, I can tell the reader which x's make it positive and which x's make it negative. So f of x is positive for, let's see, when the x is less than minus 2, when the x is between -1 and 1, and when the x is is greater than 2. All right, so that's when it's positive. You can write that in a very special way. There is a way of writing that that is called interval notation, where you write a notation that collects together without having to repeat the x or do all these less thans and whatever. And so I'm just going to do it in interval notation. I could say f of x is positive for x in. Okay, and so the way interval notation works, this is a bit like the coordinates of a point, and the left-hand end is the smallest possible number that you can have, and the right-hand end is the biggest possible number that you can have. So the biggest number I can have here is -2. And it goes all the way down as far as you want. So we can go all the way down to -infinity, but obviously it can't be equal to -infinity. And then this bit here goes from -1 to 1. And this bit here starts at 2 and it goes up as far as I like. And when I want to glue 3 separate bits together, I say a U, which stands for union. And that's interval notation. And I was also asked when f of x was negative, so I can say f of x is negative for, well, let's see, let's do interval notation for x in from -2 to -1, and also from 1 to 2. So I can do it in interval notation. I'm going to do everything in interval notation from now on, because it's just a little shorter. Okay. So that was that example. I would actually like to do a second example that has a function that has a discontinuity, a place where it's undefined. I did find the X-intercepts, didn't I? Oh, yep, there it is. Good. I've done everything that was asked of me. So let's see. Find where the graph of y equals x plus 1, x minus 3 squared over x has y non-negative. Okay, so this one's quite different from the other example. Let me just compare them. Okay. So, let's see. This one uses a y instead of an f of x. That's going to make it interesting. The f of something is a little harder to, is a little easier to write things down for. And if I haven't been told f of something, then I can't use that notation. So you're going to have to use y's. The function is different. The other function was a polynomial, and this one is not. It's a rational function, so I'm going to have to take that into account as well. It says non-negative here instead of positive and negative. So positive means positive and doesn't include 0. Non-negative means positive, or it could be 0 as well, because 0 isn't negative. That's different of the way they do it in France, but in Australia, non-negative means it could be 0 and it could be positive, and positive means that it's not allowed to be 0. Okay. All right, well, the first thing I'll do is I'll figure out when it's undefined. That's a good place to start. So y is undefined when, all right, when the denominator is 0, and the denominator is x, and so we can say when x is 0. Okay. And then we should also find when y is equal to 0. Not because they asked me to find when y is equal to 0, but just because it's going to be useful to figure out when it's non-negative, when it's positive and negative. So find when y is equal to 0, and so that means that we're going to have to solve x plus 1, x minus 3 squared over x being equal to 0. Okay, so I don't want that. There's an x on the bottom that's annoying me. If I multiply by x here and here, that x will go away from this side, and 0 times x is 0. And I'm allowed to multiply by x because I've already said that it can't be 0. It's not technically, to write this doesn't make any sense if x is 0, so x isn't 0. So I should probably write that there. Okay. All right, and this is already factorized for me, so I don't have to do any factorizing or any of that, and I'm actually allowed to just use the way that factors work with polynomials. If this is 0, then the x will be -1, and if this is 0, then the x will be 3. And the squared, well, it's just 3 again. Okay, so I've found the places where it's equal to 0. I also have a place where it's undefined, and I can create a sign diagram with those bits of information. So I'm going to do a sign diagram for what y is, because I was asked to find when y was non-negative. So a sign diagram for y. So these are the options for x, -1, 0, and 3. And it is 0 at that spot, and it's not defined at that spot, and it is 0 at that spot. Okay. So this is y up here. So we're going to slowly build that sign diagram up, and to do that we're going to need to find what y is in all of these zones. Okay, so we need to pick a number down here. Let me look at my formula. Well, picking x equals 10 is not going to help this time. It's probably just going to be better to pick a nice small number in that zone. So when x is equal to -2, y is equal to -2 plus 1 -2 minus 3 squared over -2. And actually I don't have to figure that out to know. Like, this bit's positive because it's squared. -2 plus 1 is -1, so that's negative, and that's negative. And a negative number divided by a negative number always produces a positive number. So pop that positive there. When x is equal to something between -1/2. -1/2 plus 1 -1/2 minus 3 squared over -1/2. So that's positive now. That's positive. Positive on the top, negative on the bottom. That means it's going to be negative. Okay? You notice as well that I haven't written f of -1/2 or f of -2 because there is no f in the original problem, so I'm going to have to leave it as a y. When x is equal to something between 0 and 3, 1, y equals 1 plus 1, 1 minus 3 squared over 1. That's totally positive. That's positive, that's positive, that's positive. So it's a plus there. And when x is equal to something beyond 3, so when x equals 4, y equals 4 plus 1, 4 minus 3 squared over 4. Positive, 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 it's positive as well. Okay, so a few features of what happened here that was different to what happened last time on the sign diagram. The last sign diagram I had went plus, minus, plus, minus, plus. This one went plus, minus, plus, plus. So it doesn't have to always switch between. It can stay positive. Okay. This actually happens because of this x minus 3 squared. The squared is, keeping things positive when I switch over from being below 3 and above 3. Here, this number switched over to being positive when I went from below -1 to above -1. And that would have happened here as well. It would have been negative when I was below -3, but I squared it, so it didn't matter. Okay, so what was the actual question? I had to find where the graph has y being non-negative. Okay, so let's have a look at this. Y is non-negative. For all of this, it's positive there, it's positive there, it's not negative there because it's equal to 0. It doesn't exist there, it's negative there, and it's not negative there. So y is non-negative for x in the set, it goes from -infinity up to -1, and it does include -1. So just so you know, this square bracket means that that number is included. But if you put a round bracket if the number isn't included. And you'll notice there's a round bracket here because you can't actually be equal to -infinity, it's not a number. And then we also have from 0 up to 3, and then beyond 3 as well, so all the way up as far as we want to go. But you'll notice 0 isn't included because it's not actually defined there. So I'm just going to, this is the -1 is included, and this one is the 0 is not included. Okay. Now, nobody asked me to sketch it, so I'm not going to. But actually, do you know what? I will, just because I want to make a point about something. So I know it's not actually defined when x is 0. And this time I'm going to have to be a bit more accurate. 1, 2, 3. Okay. I know it crosses the axis at both of these points. I know there is an asymptote here when x equals 0, because when x is 0, the top isn't 0, but the bottom is. So I've got choices. It's either going to go up here, or down here, or up and down, or down and up. And I could try and investigate what happens when x is close to 0, but above and below 0. But I don't have to, because I've already gone to all the effort of figuring out whether it's positive and negative. So I know that in this zone here between -1 and 0, it's negative. It can't be going up, or it would have been positive. So it must be going down. And in this zone here between 0 and 3, it's positive. So it can't be going down. It would have to be going up. So I told you earlier that you can use reasoning about what happens when you're close to the number. But you can, I told you something was happening later that might make it a little easier, and it's this. If you can figure out where it's positive and negative, then you don't have to use that reasoning about what happens when you get close. And that's a little easier, I think, this version. Now I do know it crosses, touches the x-axis here, and then it stays positive. And so it's actually going to come down here and go back up again. And over this side it's positive. I don't really know what it's going to do over here, because I haven't really investigated the other things about graphs that's coming. But I do know that when x is shockingly huge, x plus 1 is almost the same as x. X minus 3 is almost the same as x compared to the size of x. If x was like a million and 1, who cares about the 1? So if x was really huge, this is like nearly x, this is nearly x squared, and x times x squared is x cubed, and x cubed divided by x is x squared. So when x is very large, it's approximately equal to x squared. And so there's like an x squared here, and this will actually get closer and closer to the x squared. And so will this. It's a very not to scale graph at the top with the y-axis, but that's roughly what it will look like. Now, of course, with some of the tools that we're about to learn soon, we could be a bit more precise about what's going on there. Okay. So, there are two more. There are two more things about the way a graph works that I would like to talk about. And I'm going to talk about them on the computer. So remember this graph? I might just zoom in a little. Okay, so we've already talked about how to figure out when the graph is above and below the x-axis, but that certainly wouldn't tell us anything about what's going on here. And so we are going to investigate that. So if you had never seen a graph before and someone said, look, here's a graph, the idea is that when you put an x in, it figures out a y, and I connect all those points up, and that's what this is, and the axes, you know, if you sort of knew a little bit about how the process worked, but you'd never seen it, you'd look at this and you'd think, oh, okay, so it's got these humpy bits here, and look, as I move along for x going this way, it sort of goes up and then goes down, then goes up. Something weird happens in the middle, it goes up again, and then it goes down. And so I would like to know words for those things. Because if they're things I would like to describe, I need words for them. So the humpy bits, mathematicians call concavity. It's the way it curves. And so this bit is called concave down, and this bit's called concave up, and this bit's called concave down. So they're sort of the hills and the valleys. And the other thing that you noticed is that it was sort of going upwards as I moved along here and going downwards as I moved along here. They're called increasing and decreasing. So the increasing is referring to the fact that the y value increases as the x moves forwards, whereas over here the y value decreases as the x moves forwards. Okay, so we've got some terminology. We have concave up and concave down. Concave up, I remember it is like a smile. It's always concave. Concave up like a smile, concave down like a frown. Smile happy up, frown unhappy down. And so that's good. And increasing and decreasing, well, it's going up and going down. That's what those words mean. But it's a bit floppy at the moment. It's a bit fuzzy. It's not particularly precise. And mathematicians are nothing if not precise. And actually, mathematicians have this great need to talk about the function itself as opposed to its graph. I will contradict that at some point soon, actually, but keep an eye out for it. But mostly, you're interested in the function itself. And so I would like some feature of the function to be related to what that graph is doing there. Okay, so those words increasing and decreasing and concave up and concave down are things about the function. Concave up, concave down, really you can't talk about without talking about the graph. But I can talk about increasing and decreasing by just talking about the function values. And so I'd like a nice, rigorous mathematical definition of what that means. Okay, well, increasing means that if the x moves forwards, then the y moves up. And so if I have an x that's higher, then the y should be higher as well. Okay, and we are going to talk about increasing on an interval. So this is what an interval looks like. The green band there is technically not the interval. The interval is just this bit on the x-axis. But that green band helps us keep track of what the y value is doing as I move the x. So on this interval, it's not increasing or decreasing. It's sort of increasing for some and decreasing for others. We'll talk about that in a minute. But certainly on this interval just here, it's definitely increasing on that interval. No matter where I am in that interval, if the x is further forward, then the y is further up. And same deal over here. No matter where I am, sorry, this is set up so that it only works one way. No matter where I am in this interval, if the x moves forward, then the y will go down. So what I'm going to do is I'm going to turn on some things that I've forgotten I had turned off. And I'll just zoom in here. So in this interval here, no matter which 2 points I pick a point there, and every point elsewhere, if the point is further forward, then the y value is further down. And that's the same as saying that this straight line segment has negative slope. And that's going to be important soon. Whereas over here, on this interval, if my point is further forward, then the y is further up. And actually, that's true on this entire interval all the way to here. If the x is further forward, then the y is definitely further up. Even if it's here, it's a little, let's zoom in, it's a little bit further up, no matter where I am. Okay? Whereas this interval here, sometimes if the x is further forward, it's further down, and sometimes if the x is further forward, it's further up. And so it's not increasing or decreasing on this interval. You might say it's both increasing and decreasing, because sometimes it goes down and sometimes it goes up. Okay? that's my definition of increasing, and I'm going to write that down. I was up to number 3, wasn't I? So, if it's increasing or decreasing, the formal definition of it is this. A function f of x is increasing on an interval. Now that interval could be like from A to B, or it could be like from A to B, or it could be like from A to B, or any other combination. When for any x1 and x2 in the interval, that have the x2 further along than the x1, with the x2 being greater than x1, then f of x2 is greater than f of x1. So if the x2 is further along, then the f of x2 is further up. Now you might not be used to seeing them round this way, so I'm just going to write it this way. But it doesn't, well, I'm just going to keep it. But it doesn't really make as much sense in the other direction, like grammatically. Okay, that's what increasing means, and I'm just going to draw on the actual paper a picture of that, because that's on the computer. So here's our interval, sort of the ends of my interval are here, and this is x1 and x2, and this is f of x1 here. So if the x2 is further along, the f of x2 has to be higher up. So I've got some sort of wicked curve like that. It's supposed to be going up on the entire of like that. And there's f of x2 there. And the function is increasing when it goes up from one point to another. That's what it looks like. So it might, this line might cross the curve, it might do any number of different things, but it just goes up. And a function is decreasing on an interval when for any x1 and x2 in the interval with the x2 being further along than the x1, then f of x2 is less than f of x1. So as the x moves forward, the y moves down. So there's my x1, and there's f of x1, and there's my x2, and the f of x2 has to be lower. And that has to be true no matter where you are in the interval. For everything in the interval, it has to be that way. Okay. So if there's one that goes up, if there's any one line segment that goes up and any one line segment that goes down, if they both happen, it's not increasing, it's not decreasing. Okay. That's the definition of increasing and decreasing. But there was something on the picture that I wanted to talk about. I did mention it. Oh, maybe I didn't. Just let me just turn these on. Off. This point here, it's increasing for every interval on this side, and it's decreasing for all the intervals, well, nearby, on this side. And that's called a turning point. The graph turns there. It stops going up and starts going down. Turning point. This one, turning point, stops going down, starts going up. This looks weird, but it's not a turning point because it's going up and then it's still going up. And this is a turning point because it stops going up and starts going down. And a turning point has the property that every interval that ends at that spot will be sort of increasing or decreasing. And every interval that begins at that spot will be the other one. So if it either every interval that ends there is increasing and every interval that begins there is decreasing, or the other way around. Every interval that ends there, that there is an interval that ends there where it's increasing, and there's an interval where it ends there where it's decreasing, or vice versa. So that's the definition of what a turning point is. And so I'm just going to write that down too. A point A, f of A on the graph y equals f of x. So it's actually a point on the graph. Is a turning point. Oh, I should put that in capitals so that it looks like a, this is important. Is a turning point if f of x is oh gosh, it's hard to say, right? It's increasing on intervals that increasing on an interval that has it as an endpoint, and decreasing on another interval that has it as an endpoint, basically. That is, i.e., increasing on sort of BA and decreasing on AC, or decreasing on BA, increasing on AC. Okay, so picture. Here's the A and here's the B I was talking about, and here's the C I was talking about. And it's sort of increasing on this interval and decreasing on this interval. I'm just going to draw increasing here and decreasing here. And it doesn't actually have to be increasing everywhere on the other side, just nearby. Or it could be this way around. It could be decreasing on this side and increasing on this side. So there's an interval here where it's decreasing, and there's an interval here where it's increasing. And that's called a turning point. Now that's the formal definition of a turning point, but we can see it on the picture. We can say, and we can be a bit sloppy about it and say, well, it's a point where it changes from increasing to decreasing. But if we're going to be good mathematicians, we should give a very, very precise definition. Okay. Well, the other feature that I mentioned, and it was the feature I mentioned first, was concave up and concave down. And I talked about it on the graph. These places that were sort of frowny were concave down, and these places that were sort of smiley were concave up, and these places where, and look at this, it's actually frowny here. If I just zoom in on that bit, it's part of a frown. So that's concave down as well. And it's sort of frowny here, so it's concave down. So this graph is, goes sort of concave down, concave up, concave down, concave up, concave down. Soon enough I'm going to want to figure out where it switches over between concave up and concave down. So the first thing I'm going to do is just write down what I'm imagining here. So fourth property, concave up, concave down. Okay. And the idea that I'm thinking in my head is that something like this is concave up, concave down, and it reminds me of a frown. And something like this is concave up, which reminds me of a smile. But reminding you of a frown is not a mathematical definition. And so we're going to need something better than that. And so I'll show you what it is. So back when we defined increasing and decreasing, we had this these 2 points here. And we could say, well, if we have 2 points on the graph and the line segment is sort of going up, then it's increasing on that zone. Unless if all the line segments for all the points in that interval go up, then it's increasing. So I'm going to reuse this line segment as a way of trying to figure out whether it's concave up or concave down. So let's just zoom in on this bit that's concave up and think about what this means. So no matter where I move this line in this concave up zone, it's always above the graph. And that's going to provide our definition of concave up. It's a really convenient definition because it matches with the line segment that I use for increasing and decreasing. And it certainly matches with this. And also, it's nice to know that the line segment is above goes with upness. And that's kind of cool. And so that's that. But if I zoom on this bit where it's concave down, whoa, yeah. Then no matter where I move this line, it always is below the graph. Even over here, when it's very close to the graph, if I zoom in far enough, I can see actually it is below. So it's still the same deal. I still talk about regions. So on this region, because every line segment connecting 2 points on the graph in that region is above the graph, it's concave up there. Now there are some issues. At a point like, I keep doing it, don't I? On this region, it is neither concave up nor concave down. For a start, this line is both above and below the graph. So it is not concave up and it's not concave down. And some places it's totally below, and some places it's totally above. And so I could probably find regions within this region where it's concave up and concave down, but as a whole on this region it's neither. Now I should point out that it's sort of concave up in this bit and concave down in this bit. So somewhere in the middle here, the same deal over here, somewhere in the middle, between here and here, it switches over to concave up and concave down. So in this zone, it's concave up, concave down there because the line is below the curve, and it's concave up here because the line is above the curve, and it switches over somewhere in between. And that place where it switches from concave up to concave down, it just is called an inflection point. Inflection means curving two ways. Okay. So let's write all that down. Oh, okay. Now, I told you that I'd contradict myself, and I said that what I would really like is a definition that didn't refer to the shape of the graph, and I've just defined concave up and down in terms of the line being above or below the graph. Sad, but there it is, and I can define it without that, and I will, but that's not the thing that I want you to focus on. So a function f of x is concave up on an interval when for any x1 and x2 in the interval the line joining x1 f of x1 and x2 f of x2 is above the graph of y equals f of x. And what that means, so just completely formally, so that I'm not mentioning the graph at all, I could say, so to say that the line is above the graph is to say that is the point that's on the line. So for any x which is in the interval between x1 and x2, I might just say between x1 and x2, then the value of the function on that line, which is going to be this. Actually, I'm just going to need to draw a picture to make sure I get this right. So let me, there's going to be a little space here that's going to have that picture in it. Okay. So here's the picture, and my curve is going like that, and here's x1 and x2, and here's the edges of the interval that I was talking about. And here is the line segment that's joining them, and I need that to be above the curve. Sorry about that. For every possible choice of x1 and x2 in order for it to be concave up. Okay, so if I had a point x in the middle here, then if I wanted this line, I would use the slope of that line, and every time I moved across a bit, it would go down by that slope, or up if it was going, if the x1 and x2 were this way. And so what I'd be doing is I would go, those colours are very similar, I'm sorry. So the function value would start at whatever f of x1 was, and what it would do is it would add on the slope times the distance that I travelled. So the slope would be f of x2 minus f of x1 divided by x2 minus x1, and the distance that I travelled is x minus x1. So that calculation there, it's lovely, isn't it? Has to be greater than the function value. Okay, that's the formal definition. I can actually do a little bit of algebra on this to make this a little prettier, but I'm just going to leave it like that for the moment. Okay. And I should do the definition of concave down as well. So a function is concave down on an interval when for any x1 and x2 in the interval the line joining x1 f of x1 and x2 f of x2 is below the graph of y equals f of x. That is for any x between x1 and x2, f of x1 plus f of x2 minus f of x1 over x2 minus x1 times x minus x1 is less than f of x. Okay, and the graph looks like this. And here's x1 and here's x2. My interval sort of goes from here to here. And like that. Okay. And the last thing I said was that a point on the graph is called an inflection point when similar for a turning point when intervals before are it's concave up and intervals after it's concave down, or vice versa. So I'm just going to copy what I said for the other one, but make it better. So a point A, f of A on the graph of y equals x y equals f of x is an inflection point, an inflection point. Note that some people spell inflection with an x here where the CT is. Perfectly okay. You might say that it's more common in the USA to put an X than a CT, but I think I'm actually wrong about that. It's really a time thing. At some point it was an X, and at some point it was a CT, and then it was an X again. No one seems to be able to decide. You spell it whichever way you want, but please be consistent, or that's just going to annoy people. It's an inflection point if, or when, if you like, it doesn't really matter. F of x is concave up on an interval with A as an endpoint and concave down on another interval. Is an endpoint. So either increasing on BA, decreasing on, not increasing, concave up on BA and concave down on AC, or concave down on BA and concave up on AC. And so that'll tend to look like this. So here's my point, A, and it can be concave down here and then concave up. Or it could be a lot more gentle than that, and the other way around. It could be concave up here and concave down there. And a lot less obvious what's going on there, but it's still true. Okay, so one final thing to say about concave up and concave down and increasing and decreasing is that they are not directly related to each other. They are not related to each other at all. It is possible to be concave up and increasing. It's possible to be concave down and increasing. It's possible to be concave up and decreasing, and possibly concave down and decreasing. And in fact, all four of those options are here in this picture. It's concave up, it's concave down in all of this, but it's increasing here and decreasing here. And it's concave up in all of this, but it's decreasing here and increasing here. So this picture has all four of the possibilities for concave upness and concave downness and increasing and decreasing. So I'm just going to be extremely explicit about that and draw it again, that same picture. So note these combine in all four ways. Okay? So you can have concave up decreasing and concave up increasing, and you can have concave down increasing, and you can have concave down decreasing. And they are all possibilities. So concave up decreasing is this. Concave up increasing is this. Concave down increasing is this. And concave down decreasing is this. And so I like to organize them this way because either side of the smile, one's decreasing and one's increasing. Either side of the frown, one's increasing and one's decreasing. Okay. So that leaves me about an hour to talk about how increasing and decreasing and concave up and concave down are related to derivatives. Okay. Sharpen my pencil. So let me go back to my computer. Okay. So let's first look at increasing and decreasing. I'm just going to turn off the moving region. I'm going to turn off one of my moving points. Oh, nope. So I know, this is how I defined derivatives before. If I zoom all the way in on that point, the function looks straight, and that straight line that it looks like it is, the slope of that line is the derivative. So now if I just turn my moving point back on again. Oh. If it's straight, then no matter where I put these 2 points, it'll always be as the x moves forward, the y moves up. And so a straight line is that's upward sloping is always increasing. And if I've confined a derivative around a point, then there's a little zone where my function is approximately equal to a straight line, in which case it's definitely going to be increasing in that little zone. And if it's differentiable, and if the derivative is the derivative being positive means all those slopes are positive. In all those little zones, we can glue them all together and make a great big interval where it's increasing. And same thing works for decreasing. Over here. If I've got a derivative, then it's approximately equal to that line segment, and so I can glue together all these places where the derivative is negative, and those derivatives will be the slopes of these line segments because they're approximately equal to the slope of the curve, and so the derivative being negative in a region will be able to make that whole region an interval where the function is decreasing. Okay. And then being able to switch over from one to the other, here at the turning point, here at the turning point, all of these, this thing, all the derivatives will be negative over here because we know that decreasing and being able to find a derivative go with negative derivatives. And all the derivatives are positive over here, which means that the derivative is going to have to be 0 right in the middle. And if you think about it, if I zoom right into here, it'll look flat eventually, which is a 0 slope. Okay. Actually, I should have just done this. Right. So I'm going to write that down. So I'm actually up to doing derivatives and features. I might start a brand new page, actually, if that's okay. Okay, so I'm just going to start at 3 because 1 and 2 weren't about derivatives. 1 was about where it's undefined and 2 was about where it crosses the x-axis, about where it's positive and negative, and that's not about derivatives, but derivatives start at number 3 with increasing and decreasing. So this is a theorem. The other one was a definition. A theorem is something that we prove to be true. A definition is just what we say the meaning of a word is. So we know what the word increasing means. It means no matter which line segment I draw, it's always going up. And the theorem says that that's related to derivatives. So if f dashed x is greater than 0 for all x in an interval, and in particular in an open interval where it doesn't include the two ends. Okay? Doesn't really matter what happens at the two ends, it'll be fine. Then f of x will be increasing on the closed interval, including the two ends. That's the theorem. So as long as the derivative is positive everywhere on the inside of an interval, the function will be increasing on that interval, including the two ends, because you'll be able to go all the way up to the edge. Okay? And if f dashed x is less than 0 for all x in an interval, AB, then f of x is decreasing on the interval from A to B. Now there's a few things. Actually, technically you don't need it to be strictly less than 0 for every x in that interval. You just need it to be less than or equal to 0 and have at least one that's actually properly less than 0, and that'll do it. But yeah, it's a bit weird. But definitely if they're all positive, then it's definitely increasing there. And you can glue two increasing intervals together and it'll be increasing over the whole thing. So the other thing I mentioned was the turning points. How do you find a turning point? Well, it's between an interval where it's increasing and an interval where it's decreasing. So if f dashed x is positive in an interval on the right, on one side, and negative in an interval on the other, then it's a turning point. Well, I mean, we already know what a turning point is. We know that a turning point happens when it's increasing on an interval that ends there and decreases on an interval that begins there, or vice versa. And we can figure that out from the fact that that the derivative is positive and negative. But what will happen is that at a turning point, if the derivative is defined at the turning point, it will have to be 0 because the derivative goes from being above 0 to being below 0, or vice versa. So at a turning point, f dashed x is 0, or f dashed x doesn't exist, does not exist. So it is possible for the function to exist but the derivative to not exist. You haven't seen any of those. I'm not going to actually show you any of those, but it tends to happen in your graph when there's a sharp kink in your function. So it sort of like goes like that. Okay. And this looks more like that. Okay, so this is the theorem that relates derivatives to increasing and decreasing and turning points. And what I really need to do is do an example. And so I will go, for example, find where f of x, which is equal to x to the 4 minus 5x squared plus 4, is increasing and decreasing, and state its turning points. Okay. Let's see what happens when we do that. And I like to have it on the separate page so that I can move it around to remember what I was doing. Okay, so we'll find the derivative first because we know, just a second, wait. I need to know when my function's derivative is positive and when my function's derivative is negative. And the derivative is a function of its own. And I already know how to find when something's positive and negative. I find when it's 0 or when it's undefined. And then I just test points in between, and that'll be when it's positive and negative. I already did that for just plain functions. It should work perfectly well for derivatives, which are functions of their own. So I should find the derivative and do the whole sign diagram thing with that. So let's find f dash x. And so we knew that f of x was equal to x to the 4 minus 5x squared plus 4. And this is just good practice. If someone gives you an assignment or an exam question and you're going to calculate a derivative, it's a good idea to write down the function that you're calculating the derivative from, so the person reading it can see how that derivative happened, rather than trying to imagine what the original was like and compare it in their head. Okay, so the power will multiply and then the power will go down by 1. The minus 5 will still be there, it'll become a 2x, and the 4 will disappear. And so I've got 4x cubed minus 10x. Okay, and so then I should find when it was 0. So solve f dash x is equal to 0. Actually, this is a really interesting point. I have become interested in places where the derivative is 0. When I was just looking at the graph and its shape and when it was going up and down, I was only interested in places where the graph turned. And now I have become interested in places where the derivative is 0. And they're not quite the same thing. Actually, in this graph here, I can see it, that this graph here that I started with, at this point just here, the derivative is actually 0 there. If I zoom in, it'll be flat. But it's not a turning point because it's going up and then it's still going up after. So this point is going to appear, if I find all the places where the derivative is 0, this point's going to appear. And it's useful to have a name for those points. And those points are called stationary points. So I'm just going to go back here and add that in, if that's okay. So a point where f dash x equals 0 is called a stationary point. That's an important thing to know. It's called stationary from physics. If your x was the position of something, then the derivative would be its speed. And if the speed is 0, then something's not moving, so it's stationary. And it's important to put an A here. Stationary with an A means not moving, and stationary with an E means, you know, pencils and pens and that sort of thing. Yeah, so it's stationary because it stops going up, and then starts going down, so for a moment it's still, but it might stop going up, be for a moment still, and then start going up again. Okay, just that's important. So let's see. We're going to solve for f of x equals 0, which means we're going to be finding the stationary points. It may be that those stationary points might be turning points or they might not, but it's good to have a name for them. Okay, so we need 4x cubed minus 10x equals 0. I see they've both got an x, so I'll pull that out. And actually they've both got a 2. So that leaves me with 2x squared minus 5. Okay, so the 2 isn't 0, so that's fine. The x could be 0, or this thing could be 0. And this thing's only got one x in it, so the quickest way to solve it is to do the thing where you move stuff away and until you've just got x by itself. So 2x squared equals 5, x squared equals 5 on 2, x equals plus or minus the square root of 5 on 2. Okay. All right, so we have 3 stationary points, 3 places where the derivative is 0. And we want to know whether there are turning points or not. So drawing a sign diagram will allow us to figure out where the derivative is positive and negative, which will allow us to figure out where things are increasing and decreasing, which will allow us to figure out where the turning points are. So a sign diagram for f dash x, because that's what we're calculating. So this is x, and the points of interest are 0 and minus root 5 on 2 and plus root 5 on 2, and it is actually 0 at all of those points. Okay, and now I have 4 zones, 4 zones where I would like to figure out whether it's positive or negative. So I'm just gonna figure out approximately what this is with my calculator. Square root 5 on 2, well, 2.5, 5 on 2 is 2.5, and 2.5 is less than 4, so the square root of 5 on 2 has got to be less than 2, and it's also got to be more than 1. So I know it's between 1 and 2, but I'm just going to calculate it just to be sure. Plus or minus 1.58, approximately. Okay, this is an approximately equal to sign. Some people draw that differently. That's how I draw it. Okay. Therefore, I can do this. I can say f of minus 2, which I know is going to be in this zone just here. The original function, no, f dash. 4 of minus 2 cubed minus 10 times minus 2. So minus 2 cubed would be minus 8. So that's minus 32 plus 20, which is negative. Okay. Something between minus root 5 on 2 and 0 is minus 1. And so we get 4 times minus 1 cubed minus 10 times minus 1. Okay, so that's minus 4 plus 10, which is positive. F dashed of something between, that's 1. 4 times 1 cubed minus 10 times 1. Well, that's going to be negative. And f dashed of 2, because I'm calculating f dashed of x, putting it there reminds me what I'm calculating, is 4 times 2 cubed minus 10 times 2, which would be 32 minus 20, which is positive. Okay. And so it goes plus, minus, plus, plus, minus, plus, minus, plus. Right, and so I can figure out where it's increasing and decreasing. Let me just check what the actual original question said. Increasing and decreasing. Okay, and it wants the turning points too. So at the moment I can tell it's increasing here, decreasing here, increasing here, decreasing here, increasing here. And therefore, since it's decreasing before this and increasing after, this is a turning point. Since it's increasing before and decreasing after, this is a turning point. Since it's decreasing before and increasing after, this is a turning point. And so, cool, I can tell that they are turning points. They really are. And technically, the definition of turning point said that it was a point on the graph. And so I'm going to have to give the actual coordinates. So let's see. Let's just find the turning points. So when x is equal to minus root 5 on 2 f of minus root 5 on 2 is minus root 5 on 2 to the 4. This is the original function now, because I'm finding out the y-coordinate. Minus 5 times minus root 5 on 2 squared plus 4. I need that root to go all the way to the bottom, or the 2 wouldn't be included. So the 4 will make the minus disappear. When I square something and then square it again, that's the same as 4, so it's going to be 25 on 4 minus 5 times 5 on 2. And so we want that to be on 4, so that would be, and that's 2550. 4 plus, and I guess this would be 16 on 4. So 25 minus 50 is minus 25. Minus 25 plus 16 would be the same as minus what I get when I do 25 minus 16, which is 9. So I get minus 9 on 4, which is in fact equal to minus 2.25. I happen to know that fact. Okay, x equals 0. F of 0 is 0 to the 4 minus 5 times 0 plus 4. And x equals plus root 5 on 2. On 2 to the 4 minus 5 root 5 on 2 to the 4 plus 4, which would be the same answer we had before, because the minuses behave the same way inside the powers of 4. Okay, so turning points are minus root 5 on 2 minus 9 on 4. 0, 4, and plus root 5 on 2, minus 9 on 4. Okay, and I haven't quite finished yet because I was asked where it was increasing and decreasing. Okay, so increasing and decreasing is about intervals, right? You can only say that it's increasing or decreasing on an interval, and so you should really say it's increasing on these intervals, and so I can say also f of x is increasing on any interval contained in here. So I can do a set that contains all of the places where it's increasing. So let's see. It's decreasing there. So everything from minus root 5 on 2 up to 0, and anything from root 5 on 2 to infinity. But I don't put a square bracket on infinity because you can't actually be equal to infinity. And it must be decreasing on the other bit. And fx is decreasing on any interval contained in the decreasing bit, which was minus infinity up to minus root 5 on 2, and from 0 to root 5 on 2. Okay. Okay. So the question didn't ask me to do this. I've done everything the question asked, actually. Didn't ask me to do this, but it's worth pointing out that I can have a really good idea of what this graph is looking like, because so far I have figured out where its x-intercepts are. And if we go back to when I calculated that, that was right near the beginning. Its x-intercepts were at minus 2, minus 1, 1, and 2. 1, 2. So they're the x-intercepts. And I know that its turning points were at minus root 5 on 2, which was approximately 1.58, which is about here. And the y-coordinate was minus 2.25. So 1, 2, about here. And then the y coordinate, so same deal over here. And the other turning point was at 0, 4, which is 1, 2, 3, 4, about there. And so my graph is going to go something like that. Now, there's somewhere in the middle here, it must be, there must be an inflection point, because it looks concave up here and concave down here. There must be one somewhere in the middle there. Okay, but we need to know how to find the inflection points, which means that we need to know how to do that with derivatives. I've got about half an hour to do that. My recording in this room is going, I have to set a time, so if I don't finish in time, it'll just cut off. So here's my graph. I'm going to need to turn, I'll just move these out a bit. Okay, so if it's concave up, I know that no matter which line segment I draw, it's always going to be above the graph, and I need to somehow figure out how that's related to derivatives. Okay, so well, derivatives are the slope of the line, slope of the curve. So, the slope of the curve is going to be about like this. Just give me a second and I'll put that in. So we have a line that passes through the point that, and it has slope f dash a. All right, that's the curve there. All right, and then I'll just do the same thing down here, but for the other point. Okay. Just make them both blue, hey? All right. So down here, this slope is definitely less than that slope because it's negative and that one's positive. And this slope is more than that slope because this one goes across this much and then goes up that, and this one goes across the same amount and goes up faster. So at both ends of this, the slope of the graph is the slope of the graph, which is this tangent line here, because we talked about that in a previous seminar. The slope of the graph is higher, is lower than the slope of the line here, and higher than the slope of the line here. So on any one of these line segments, the slope increases between here and here, no matter how small that line segment is. So the slope of my graph, if it's concave up, the slope of my graph on any interval is increasing. But the slope of my graph is the derivative. So the derivative is increasing. But I know how to tell when a function is increasing. A function is increasing when the derivative of the function is increasing. So if the derivative is increasing, then the derivative of the function is increasing when the derivative is positive. So if the derivative is increasing, that means the derivative of the derivative must be positive. So that's what it means. And we can actually get that directly from the definition we had before, because we can rearrange it to get slopes from the definition we had before involving this. So document camera. When we did the definition of concave up and concave down, see this thing here? If I subtract this over there and then divide by this, I get two slopes, and one slope is more than another slope. And so in concave up and concave down is actually, even though it looks like it's about lines being above, we can pitch it to be about differences in slopes. So because of that, because of the way the picture works and the way that the slope on one end is, it has to be lower than the slope on the other end if it's concave up, and the way that if it's concave down, Let me just put it closer to the turning point so it's easier to see what's going on here. See, the slope here is steeper than this slope. Sorry, this purple slope is steeper than that, but a steeper negative slope is a lower slope. So the slope of this line is lower than that, but the slope of this line is higher than that, and so the slope has to be increasing because it goes from lower than the line to higher than the line. So, sorry, the slope is decreasing. Like it was this gentle here, and it's even more negatively sloped before, so the slope has gotten more negative, so it's decreasing. But even on this side, the slope is really steep here and less steep here, so it's become less positive, so it's decreasing. So number 4 and concave down, we have a similar theorem than we had before. So my theorem goes, if the derivative of the derivative, which is known as the second derivative, is greater than 0 for all x in an interval, and it's specifically an open interval, then f of x is concave up on the closed interval. And if the second derivative is negative for all x in an interval AB, then f of x is concave down. And isn't it nice that positive goes with up and negative goes with down? Very convenient. And so we know that if it's concave up on one side and concave up on the other, that's when an inflection point happens. And an inflection point, therefore, it means that the second derivative is usually positive on one side and negative on the other. And if you move something from being positive to being negative, that will make it 0. Just let me write this. I want to write it exactly the same way as I did it for first derivatives. At an inflection point, f dash x, f double dash x will be 0, or f double dash x won't exist. So exactly the same way that it works for increasing, decreasing, but with the second derivative. The derivative of the derivative. And the reason that works is, well, the slope is increasing in a concave up region, and so if something's increasing, its derivative should be positive, so the derivative of the derivative is positive. Okay, but I just want to point out, back when we had increasing, decreasing, a turning point was a place where the derivative was 0, but a place where the derivative of 0 isn't necessarily a turning point. And we had a special name for a place where the derivative is 0, which was a stationary point. Well, there just isn't a name. I'm sure there is, but nobody uses it anymore. So there isn't a name for places where the second derivative is 0 that aren't inflection points. So I'm sorry about that. Okay, so let's run with it. Let's continue our example with that same function. Find where f of x is x to the 4, which is x to the 4 minus x squared plus 4, is concave up and concave down, and state its inflection points. Okay. So, well, if we want the inflection points, we are going to need to find the second derivative. So, because it was pages ago when I did this, I will just repeat it. And that's good practice. This became 4x cubed minus 10x, I believe. And the second derivative would be 4 times 3x squared minus 10, which is 12x squared minus 10. So we want to solve f double dashed x equals 0, which means that we have 12x squared minus 10 equals 0. And the reason we want to know this is because that's when it will switch between concave up and concave down. Okay, and so we'll go 12x squared equals 10. I can divide them both by 2, and now that's 5/6. And so x would be the square root of 5/6, but it could be the positive or the negative number. So same deal as before. I need to know when it's positive and negative, which means I could find out when it's 0 and then test points in between with a sign diagram for f double dashed x. Don't really want to underline that. It's not worth underlining. Okay, so these are the x's. The places we're interested in are minus root 5 on 6 and plus root 5 on 6. Okay, and 0 is actually not an interesting point for us. It didn't come up in this working. So let's see, f dashed, double dashed of a number over here. Well, root 5 on 6, actually just let's write down what that is approximately. 0.913. Okay, so we can go to minus 1 because that's definitely less. And 12 times minus 1 squared minus 10 would be 12 minus 10, which is positive. And f double dashed of a number in this zone is 0, which would be 12 times 0 squared minus 10, which is negative. And f double dashed of 1 would be 12 times 1 minus 10, which is positive. I might just remove that mark. Okay, and so this is my sign diagram. I was calculating f dashed x, so I should put it on the diagram to remind the reader that that's what it is. And so I can tell that since the second derivative is positive here, it must be concave up there, and concave up for any interval there, and concave down for any interval inside that middle bit. So f of x is up on any interval in this set, so anything from minus infinity up to minus root 5 on 6, and we are allowed to include that point. And any interval from root 5 on 6 to infinity. Just be careful, some people talk about concave up and concave down differently than the way I do, and they talk about it being concave up and down at a specific point, and so they won't include these, there'll be round brackets. But I think this is the most correct way. And f of x on any interval inside, now let's see, just from minus root 5 on 6 to root 5 on 6. And the inflection points, well, they really are inflection points, so it's concave up here and then concave down, so it's a proper inflection point. It's concave down, then concave up, proper inflection point. If they'd both been plus, it wouldn't have been an inflection point because it didn't change. Okay, and so the inflection points, let's just find the inflection points. F of minus root 5 on 6 is minus root 5 on 6 to the, I need the original function, to the 4, minus root 5 on 6 squared plus 4, which would be 5 to the power of 4, which would be, no, it wouldn't be. The root 5 squared would be 5, so 25 on 36 minus 5 times 5 on 6 plus 4. So we want 25 on 36 minus, we want to times that by 6. Oh gosh, I'm just going to use a machine really. 25 on 36 minus 5 times 5 on 6 plus 4. And can I get it to tell me what that is as a fraction? Where's my fraction to decimal button? Most of them have one. Well, it's got to be in sixths, right? In 36, so that's 19/36. Okay, which is approximately 0.528. And f of plus root 5 on 6, well, this will work exactly the same way, right? With the plus there and the plus there, the squared and the quarter will do the same thing. So that'll also be this. Okay, so the inflection points are minus root 5 on 6, 19 on 36, and plus root 5 on 6, 19 on 36. Which means that I can actually draw my graph now. I had a graph earlier, wherever that was. Here. I now know the exact location of these inflection points. It's at minus 0.9-ish, up a bit, like that. So I can draw them in. 2, 3, 4. 1, 2. And it was at down here at minus 2 1/4. It was up here at 4, and then this was at minus 0.913, so it's about here, and then it was up at 0.58, I think, so about there. Okay, so this is a sketch. All right, and that's doing all the things it should do. And you could, if you wanted to, label all of these points and tell the reader what they were. Right, well, I have about 13 minutes, which is enough time to do one more example of this sort of thing. And I just need to find where I wrote down the example that I wanted. I'm going to do one that isn't a polynomial so that we can see this thing, and we're going to do the entire thing together, all of the concave up and concave down and turning points and whatever, all in one go. So sketch a graph of y equals 2 minus 3x minus 4 over x take 5. Really hope this is going to work nicely. Showing all intercepts, x-intercepts, turning points, and inflection points. So we are going to have to figure out where it's increasing and decreasing, or we won't know where the turning points are. And we're going to have to figure out where it's concave up or concave down, or we won't know where the inflection points are. Okay, so here we go. So to find the x-intercept, I'm going to have to find out where y is equal to 0. So